So, hello everyone. I'm glad to see so many people here, especially when there is zero dependency Python next door. So thank you for attending. So as was said, my name is Jan Vandrol, and I'd like to show you a little bit of our research we do at St. Andrews. It's basically a part of the same science project that my predecessor here spoke about. But for those of you who weren't there, I'll repeat a bit. So we are trying to figure out how much we can use VGI data as a supplement for basically census data and any other governmentally gathered data. So we would like to figure out if we can get from GPS trackers, for example, points of interest within a city or basically any environment you live in, or if we can gather any pointers about human behavior. For example, if you live close to one shop, why would you go to half across the city to visit another shop? Why would you do it? Is there anything interesting there? Why would you waste your time? Which is basically what commuting and time allocation. And there are many other things that you can figure out when looking at the VGI data. For example, traffic data. You can see where people stopped at the traffic lights or at a jam. You can see how long it took them to basically get on the road again. So it can be used for these purposes also. So what kind of data we have? There was a survey that ended earlier this year. We gathered data from 206 users that were required to have a tracker for full 7 days, basically full week, and the tracker had 5-second sampling period. Of course, when it stopped moving, the tracker turned itself off. So it's still a lot of data. When you filter it by HDOP to basically filter any data that are not exactly accurate, you'll end up with 4 million points. So we have plenty of data to work with to see how users behave on their daily basis. So we get this huge mess of points within a city of Dunfermline. Now, what can we do with it? What can we find out? So normally, what many studies do, they just do KDE, kernel density on the data. I see, okay, so we have what, 1, 2, 3, 4, 5, 6 hotspots here. Job's done. We can pat ourselves on the back and we can go have a beer or something, right? But since I have to talk for at least 15 more minutes, I'll show you basically another approach. So as an input, we can use in our tool either CSV, in which we gain the data in from the GPS trackers, or thanks to the guys that made PySHP, we can use shapefiles. And also using PsychoPG2 library, we can also store and read data from PostGIS database. And basically all we need is a timestamp, speed, position, and if there are more users within a file, some kind of a user ID, in which case it just loops through every user. So what can we do with this mess? Well, first, we need to somehow segment the user trajectories into some small manageable parts that are somehow in the same attribute, that have same attributes. Sorry. So, for example, we need to find segments that are car travel, that are walk, that are stops, etc. So how do we do it? There are, of course, many different approaches. We could just do a buffer and be done with it, see how many points around we have, see, yeah, okay, so we have many points, this is probably a stop. But there are other ways to approach this also. What we do is we do not depend on time or speed. We take in spatial data. So you can see we connect all points within one user, into one large trajectory, for example, that spans whole 7 days. And what we do is for each point, we calculate something we call signal strength, where we go 50 meters. That can be, of course, changed within the script, for example, for 20 meters, but we found that 50 meters is more or less ideal for our purposes. And we go 50 meters in each direction, and we count number of points. So it's not just about, as we saw here, it's not just about doing a buffer. It's going through the line. So when we can see here that if you take this point, if you go by line by 50 meters, it will stop much sooner than it would normally do with buffer. And instead of 18 points, we have about 10 within this. So what we get after we cut the segments, each time the signal strength rapidly drops or rapidly increases, is really nice segments. I don't know if you can properly see it on the screen, but you can see that here is one segment, basically probably some kind of fast travel. Here, user started walking, maybe continued here, then stopped here, I guess for a game, and walked here, got on in a vehicle, and drove off somewhere else. So we have the segments now, but now we need to basically automatically figure out what the user did. Basically, what I just said, what I implied, we need to somehow automatically create. So next step is identification of these segments. We have two steps in the identification. First is basic, and then it's advanced. The basic just identifies the most basic classes we have, basically stop, walk, run, and vehicle. When this is done, you can run the advanced identification, and you can get more precise idea of what the user was doing. For example, stop then becomes either stop, home, bus stop, train stop, shopping, or traffic. Walk, run remains walk, run, because there is not much we can do about that. And vehicle can be distinguished into car, bus, and train. So basic identification, how do we do it? There are 3 options. 2 are all right, 1 is terrible, and for some reason this screen you can't see the second option, but I'll tell you about it. So first is decision tree. This is kind of old approach, and it's kind of rigid in a way, because sometimes the data is not as accurate as it should be, and you get, even when you're stopped, you get speeds, for example, for 5 kilometers per hour, which is not true, but still, if you try to use decision tree, it can go very, very wrong. But it is possible. It is. We've done it before in the beginning, and it worked okay. Second one, that you can't see for some reason on this screen, is unsupervised learning, which we used for which we used library of scikit-learn. But unfortunately, it almost never can guess the right class. So we have abandoned it. It's still in the code, but we are no longer using it. And third one, which is now our go-to approach, is supervised learning via neural networks. This approach has yielded the best results of all these. We have created our own training data set, and when you start using supervised learning within our tool, it is automatically initialized with those values inside. You don't have to train it in any way. It's just prepared and good to go. So when you try to classify the segments, it will become this. So this is the same scene as previously, but now it is correctly classified. So you can see red is a vehicle travel, yellow is walk, and blue is stop. So now we can apply that. Probably last time we went the other way. Actually, the user came in via bus, got off, walked to the stadium, stopped there, watched the game, walked back, and now here he stopped and waited for the bus, and then rode off. So that's basic identification. Then, in advanced identification, we have several steps that we use. First is home search. It is basically time-based. We look at the amount of days that user had his tracker, and then we try to see if there are any very long stops within those 7 days. If we find them, then we expect them to be home. So if you never live at home, if you just go straight to pub after work, then it will not work so very well for you. But under normal circumstances, it usually works very well. But unfortunately, I cannot show you the map that we've created to show how well it compares to real locations because of confidentiality issues. But you'll just have to trust me on this. So within 50 meters, we have allocated 71% of all homes. That's, of course, geocoded from Google, so the Google itself is not exactly precise, so we have some more leverage there. So within 100 meters, we have 83%, and in 200 meters, we have almost 90%. So I'd say it's usually a good guess we have. For work search, we employ a very similar algorithm. Again, we look at large gaps, but we assume that not every day you stop at work. Most people take a day off, they have weekends, etc. So we assume there are less huge gaps in your daily regime for work. Of course, if not enough stops are found, user is considered unemployed or retired, which in our case, with our data, were a lot of people, unfortunately. So we can't really say how well we have nailed this one, because about, I believe, 70% of all people are retired. So this needs a little more work, a little more research. Commuting is an interesting one. We use external layer. UK has very good layers when it comes to bus and train stops. So we just pull the data from their services and compare locations of their bus stops or stops in general to our stops. And if it is within a certain amount of meters or within a certain distance, we consider stop to be a wait at the bus station or bus stop. And once we find one bus stop, we consider the next vehicle travel to be basically a bus ride to the next station, etc. In case of trains, we can compare it to the railway as well, because we also have that layer. So that's quite interesting. I'm not sure if US have the same kind of layers available, but in UK it works very well. Also, there is in the future possibility of checking which exactly line was used. Problem is not every bus stops at every station or at every stop, so it's kind of hard to cross-check which exactly is the number of the bus. For shopping, right now we are using custom layer that we have created, but we are looking into using OSM maps for this, since they include shop tags. And we could do basically the same thing as we've done with commuting. That means if a user stops next to the shop, he probably is shopping. Or if he walks next to the shop, he's probably window shopping, or maybe he's intending to go in there. So for one user, for example, I hope you can see it properly on the screen, we have found these stops. These are all stops for one user. I will not show you the trajectories, how we got there, because it would be less clear. Out of all these stops, these are classified as bus stops. These are classified as shops, which is kind of strange because the user lives close to different shop, and he commutes a very long way to get to the shop in the north. So there must be something going on there. Maybe they have some very good meals or something. And these are considered traffic stops. Whenever there is a very short break in the vehicle transportation, we consider it to be a traffic light, traffic jam, or something similar. So we not only we know that someone traveled from point A to point B, we know how long, for example, he stood on the roundabout or waited for the traffic light. These last points we couldn't classify, so we expect them to be recreational points. As you can see, these points, for example, are the stadium that we've looked at previously, so we know that the user probably frequents this place very a lot. So with this amount of points, we can now start inferring some kind of information about human behavior, about time allocation, about commuting for each user. For each stop, geocoding is also available. We are using Nominatim service. Previously, we've started using Google, but it got angry with us for mining their database, so we stopped. It is a potential source of information. Of course, it doesn't work very precisely because, as it often happens, the stop is not exactly at the point of the stop. It's usually, 50 meters in one direction or the other. So the data we get from geocoding cannot be trusted, but it is still a good value in case we get it right. Well, the newest feature we have is a trip summary, which is basically a text file with list of activities, how it went from day 1 to day 7. It serves as a summary that you can just look at and see. Okay, so he drives a bus a lot, visits a shop often, but also it serves as a quality control because still this algorithm is not perfect, and there are often, for example, walks that take 10 hours for no reason. But it looks something like this. Normally it's a text file, but I've put it into a table. So we have start and end, time in seconds, how long it took for a user to get from point A to point B, and what mode we've detected. So someone stayed at home from 9 to 1 o'clock, then waited on a bus stop. So seems that he has a bus stop very close to home, and rode the bus, and then took a walk somewhere, etc., etc., and probably there was a shopping trip after that. In the future, we would like to try this on a different data set because still we got probably most of the people we've got were retired people, and we need to figure out if this algorithm works well for normally employed people and workaholics, etc., etc. So that would be interesting to see. The second thing is optimization. Now, for each user, it runs from 1 to 5 minutes, so we need to make this faster. Interactive visualization of results. Same as my predecessor said, we need to visualize what we found out. Right now, it just outputs shapefile, or it outputs into PostGIS database, so it's not ideal. And last thing, support for multiple projections. Right now, we are still studying case in UK, so we're just using the one. But it would be nice if we could support multiple projections at the same time. So thank you very much, and if you have any questions.
Thank you, Jan. That was a lovely, interesting talk. Are there any questions? Put your hand up.